This is the second part of the module on energy analysis for closed systems. Previously, you've been introduced to a few laws of thermodynamics. The first law being discovered first is very important. It states that energy is conserved. It cannot be created or destroyed. So for a closed system, we have the net energy transfer by heat and work interactions, which is equal to the change in internal energy, the change in kinetic energy, and the change in potential energy. Among other energies, too negligible, and they're normally ignored in our thermodynamics analysis. And if the closed system is stationary, then the change in kinetic energy and the change in potential energy would have been zero. So here, the conservation of energy stated in a rate form is given by 412. See, the unit is kilowatt, which is kilojoule per second. For constant rates, for the total energy during an interval time delta t, then you have 413 with the units kilojoule. And sometimes energy per unit mass is used. Then you have kilojoule per kilogram given by 413. So any one of these would have been your energy analysis for the system. Now for closed system undergoing a cyclic process, what is a cyclic process? We have a series of many processes, say n, where the system is returned to its initial state. If you have only two processes, minimum in a cyclic process, then going from state 1 to state 2 and back to state 1, so the change in the system would have been zero. So you have the change from state 1 to state 2 added to the change from state 2 back to state 1 would have been zero total. If you have several processes up to n, so you can determine the change of the energy of the system being still equal to zero because the initial and final state of the system is the same. Again, let's have a look at this 233 introduced in your second module. Q is positive coming into the system, Q net in, and W is negative, net out, down by the system. So thus we have this change in energy of the system being the Q net in minus W net out, which is equal to the change of internal energy, the change in kinetic energy, and change in potential energy. So always include all the three terms, even though most of the time your closed system is stationary. So with the change of energy of the system being zero, you end up with Q net in being equal to W net out. It's simple. Now, note that Q net in is Q in minus Q out. So we assume here the net summation is net in and summation of work is out. Now, from the conservation of energy previously for closed system with no mass crossing the boundary, this is the equation that you will see often in our energy analysis of closed systems. Now, if one does not know if the net is in or out, and we have used this equation, and in the end you get your Q net in negative and W net out to be positive, then means that initial assumption in direction is incorrect. So that means if you here assume is positive, but you got a Q to be negative, that means the net is going out instead of in. Specific heats, C. Now, it takes different amounts of energy to raise the temperature of a substance by 1 degree. Different amounts. So it is good to have a property to compare such capability. The capability to raise the temperature of the substance requires different energy. The specific heat, there are two kinds: specific at constant volume and specific heat at constant pressure. Notice the subscript. CV is the energy required to raise the temperature of the unit mass of a substance by 1 degree as the volume is maintained constant. See the subscript B there is given by 419. Meanwhile, the CP is the energy required to raise the temperature of the unit mass of a substance by 1 degree as the pressure is maintained constant, given by 420. Note that there is an error in the eBook. 420 is DH instead of DU. Now, CP is always greater than CV because at constant pressure the system is allowed to expand. the energy for the work is supplied. Yeah. For constant volume, the boundary work is 0. Yeah. Both Cp and Cv are properties of the system, intensive properties of the system. They are temperature dependent. It's very important to determine at what temperature you are obtaining the Cp and Cv. Yeah, at. So this equation 419 and 420, yeah, for Cp, Cv, yeah, are property relations, and they are actually independent of the type of processes. So why do we define them at constant pressure and constant volume? Well, because that's how their values were obtained experimentally earlier with earlier researchers. Yes. Internal energy, enthalpy, and specific heats of ideal gases. Now, Joule demonstrated in 1843 that internal energy is a function of temperature, it's given by 421. So, using the definition of enthalpy and the equation of state of an ideal gas, enthalpy definition is given in module 3. Yes. So, you can substitute the definition there, and since U is a function of temperature and PV for ideal gas is a function of temperature, and you may conclude that H is also a function of temperature, yeah, since R is a constant. So U and H depends only on temperature for an ideal gas. So therefore CpCv also depend at most on temperature only. Yeah. So they have fixed values regardless of the specific volume or pressure. Now from 419 and 420, yeah, so you have removed the subscript V and P, get 423 and 424. Now to get the change, yeah, in internal energy and the change in enthalpy, yeah, you may use 3 of these approaches. Yeah. The first approach is obtaining the change from tabulated data. Yeah, so most accurate and easiest, yeah, if you have extensive tabulated data. Yeah. The second approach is integrating 423, 24 with 423 and 24, yeah, with Cp, Cv functions of temperature. And the third approach is using average values at the average temperature. So the first approach, you may get the data for number of gases that has been tabulated over small temperature intervals. Now, the use of ideal gas specific data is limited to low pressures, but it can be used at moderately high pressures with reasonable accuracy, as long as the gas does not deviate from ideal gas behavior significantly. Now, equations 423 and 25, 26 here may be solved if we know the respective heats as a function of temperature. Yeah. For most gases, Cp, Cv can be replaced by the constant average specific heat values. Yeah, this is a third approach. It's the simplest. Yeah. Not as accurate as the first and second approach. Now, the average specific heats may be obtained at the average temperature, or for the case when the final temperature is unknown, they may be obtained at the initial temperature. Note that the ideal gas specific heats for monatomic gases such as argon, neon, and helium remain constant over the entire temperature range. Now, equations 427 and 428 are valid for any ideal gas undergoing any process, not just for constant volume and constant pressure. So with H is equal to U plus RT, you can differentiate both sides, and using the definition, the third approach, here from 423 and 24, you can get 429, which is Cp is equal to Cv plus R. It means R is available, so if you know Cp or Cv, you may get the third parameter from this equation. Then there's the ratio of specific heats, K, given by 431. Some books define K as a gamma instead. Yeah. For monatomic gases, K is essentially constant at 1.667. So many diatomic gases, including air, have a specific heat ratio of about 1.4 at room temperature. Internal energy, enthalpy, and specific heats of solids and liquids. Previously, in the preceding discussion, it was for ideal gases. Now, the specific volumes of solids and liquids essentially remain constant during a process. So you don't need the subscript P or B, it's just C. It's given by 432. Like those of ideal gases, the specific heats of liquids and solids, which are incompressible substances, depend on temperature only. Yeah, so just you see average, and then you can have H is equal to U plus PV. Yeah, you take the derivative of the terms dH, but for incompressible substance, dV is equal to 0, and that's when you integrate, you get 437. So for solids, the term V delta P is insignificant. So delta P is insignificant for solids and liquids. So you have the change in enthalpy approximately equal to the change in internal energy, which is approximately equal to Cp delta T. For liquids, two special cases are commonly encountered. The constant pressure processes, as in heaters, so delta P is equal to 0 and delta H is equal to delta U. And for the second case, constant temperature processes, as in pumps, delta T is equal to 0, and consequently you got delta H is equal to V delta P. That wraps up the module on energy analysis for closed system.